What do we mean when we say the universe? It's everything: stars, planets, and the vast dark spaces in between. Scientists define it as all of space and time and all of their contents. This includes planets, stars, galaxies, and all other forms of matter and energy. It's the entirety of existence that we can, in principle, observe or interact with. Think of it as our ultimate cosmic address, the biggest neighborhood imaginable. Our current best understanding of how our universe began is the Big Bang Theory. About 13.8 billion years ago, everything we see, all matter and energy, was squeezed into an incredibly tiny, hot, dense state. Then it began to expand. This wasn't an explosion happening space like a firework. Instead, it was an expansion space itself. Every point in space began to move away from every other point. As it expanded, it cooled. This allowed energy to transform into matter, forming the first atoms, mostly hydrogen and helium. These atoms eventually clumped together to form stars and galaxies. When we look out into space, we are also looking back in time. Light travels incredibly fast, but space is vast. The light from distant galaxies has taken billions of years to reach us. This means there's a limit to what we can see, called the observable universe. It's a sphere around us, with a radius of about 46.5 billion light-years. But is this observable bubble all there is? Or is it just our local patch in a much larger, perhaps infinite, cosmic expanse? The idea that our universe might not be the only one is known as the multiverse concept. This isn't just a wild flight of fancy dreamed up by science fiction writers. In recent decades, the multiverse has become a serious topic of discussion among physicists and cosmologists. It suggests that our universe could be just one small part of a much larger collection of universes. Each of these other universes could be incredibly different from our own, or perhaps surprisingly similar. Several of our most promising, though still unproven theories in physics, seem to naturally lead to the conclusion that other universes should exist. These theoretical hints are compelling enough to make scientists take the possibility of a multiverse very seriously, even if direct evidence is currently lacking. There are actually several different types of multiverse theories, each stemming from different branches of physics. The significance of the multiverse concept, if true, would be profound. One of the most compelling multiverse scenarios comes from the theory of cosmic inflation. Inflation proposes that in the very first fractions of a second after the Big Bang, the universe underwent a period of incredibly rapid exponential expansion. This burst of expansion is thought to have smoothed out the universe, explaining why it looks so uniform on large scales today. The idea of an inflationary multiverse arises if this process of inflation, once started, doesn't stop everywhere at the same time. This is called eternal inflation. Imagine inflation as a vast, energetic field driving the expansion. In some regions, this field might decay, causing inflation to end and a universe like ours to form, a bubble of normal space-time. However, in other regions, the inflationary field might continue to drive expansion. These regions would keep inflating, creating more and more space. And within this ever-expanding inflationary sea, new bubble universes could constantly be forming. Another fascinating path to the multiverse comes from the world of quantum mechanics. This is the theory that governs the behavior of matter and energy at the smallest scales, atoms and subatomic particles. One of its core principles is superposition, where a particle can exist in multiple states or locations simultaneously until it's measured. Think of a spinning coin. It's neither heads nor tails until it lands. The puzzle arises when we make a measurement. When we observe a quantum system, its superposition collapses, and it settles into one definite state. For example, an electron that was in multiple places at once suddenly appears in just one spot. In the 1950s, a physicist named Hugh Everett III proposed a radical solution, the many worlds interpretation, MWI. Everett suggested that when a quantum measurement is made, the universe doesn't just pick one outcome. Instead, all possible outcomes actually happen. Each outcome occurs in a separate, parallel universe that branches off from ours at the moment of measurement. So, if a particle could be in location A or location B, the universe splits. In one universe, you find it at A. In another, identical universe, a version of you finds it at B. Section 5. Numbers and Realities, the Mathematical Multiverse. Let's venture into an even more abstract realm of multiverse theories, the mathematical multiverse. This idea, championed by physicist Max Tegmark, takes the connection between physics and mathematics to its ultimate extreme. Physicists use mathematics as the language to describe the universe. But Tegmark asks a profound question. Is mathematics merely a tool we invent to describe reality? Or is mathematics itself the fundamental reality? What if every self-consistent mathematical structure corresponds to a physically real universe? This hypothesis posits that all mathematical structures that exist in an abstract sense also exist physically as separate universes. This is the most encompassing type of multiverse imaginable. It includes universes governed by entirely different mathematical equations, perhaps with different numbers of dimensions or entirely alien forms of physics. Section 6. Vibrating Possibilities, the String Theory Multiverse. String theory offers yet another perspective on the possibility of multiple universes. The fundamental idea of string theory is that the elementary particles we observe, electrons, quarks, photons, are not point-like dots. Instead, they are unimaginably tiny, one-dimensional vibrating strings. Different vibrational modes of these strings correspond to different particles with different properties. One of the most striking features of string theory is that it requires more spatial dimensions than the three we experience: length, width, and height. Most versions of string theory predict the existence of 10 or 11 spacetime dimensions. The way these extra dimensions are curled up is described by complex mathematical shapes known as Calabi-Yau manifolds. Section 7. Peeking through the veil, the challenge of proof. The grand ideas of multiple universes are undeniably captivating, sparking our imagination about the true extent of reality. However, for any scientific theory, the ultimate test is evidence. And this is where multiverse theories face their most significant hurdle. How can we possibly detect or prove the existence of other universes if they are, by definition, separate from our own? Some scientists are exploring potential indirect ways to find evidence. For instance, if our universe collided with another bubble universe in the distant past, it might have left a subtle imprint on the cosmic microwave background radiation. Another idea is that gravity, unlike other forces, might be able to leak between dimensions or universes, potentially leading to observable anomalies in gravitational measurements. A core tenet of the scientific method is falsifiability. Many multiverse proposals are difficult to falsify directly. Section 8. Our Place in the Grand Tapestry. Philosophical Ponderings. The possibility of a multiverse doesn't just stretch our scientific understanding, it profoundly impacts our philosophical outlook on our existence and our place in the cosmos. If our universe is merely one among countless others, perhaps an infinite number, does that diminish our significance? The multiverse concept could be the ultimate step in this cosmic decentering, suggesting our entire universe is just a speck in a much larger reality. This leads us to consider the anthropic principle. This principle notes that the physical constants and conditions in our universe appear to be incredibly fine-tuned to allow for the existence of life as we know it. If there are countless universes, each with different properties, then it's not surprising that we find ourselves in one that has the conditions necessary for our existence. We simply wouldn't be here to observe it otherwise. Section 9. The Unfolding Mystery, What Lies Beyond Our Sight. We find ourselves at a truly fascinating juncture in the history of science. The concept of the multiverse, in its various forms, represents one of the most profound and mind-expanding ideas that humanity has ever contemplated. It challenges our intuition, our common sense, and even the very definition of what constitutes reality. The human quest for knowledge is relentless. We strive to understand our origins, our universe, and our place within it. The journey to explore the multiverse, even if only theoretically for now, is a testament to this enduring curiosity. Whether these other universes are ultimately proven to exist or remain in the realm of speculation, the act of considering them expands our intellectual horizons. It forces us to confront the limits of our current understanding and to seek new ways of thinking about the fundamental laws that govern existence. As we continue to peer deeper into the fabric of reality, what other astonishing possibilities await us just beyond the edge of our current sight in the unfolding mystery of existence?